Hey, today we're going to be talking about friction, and friction is a vector quantity that a surface encounters when moving against another surface. When I put my phone down on this surface, it appears that the phone is touching the armchair at every single point, like in this picture. But in reality, it's touching at a couple points. And then some surfaces touch at a few points, and some surfaces touch at multiple points. And surfaces that look like this are going to have less friction, and then surfaces that look like this are going to have more friction. Static friction is the force of friction between a stationary object and a surface. And here's the equation for static friction. It's just the coefficient of static friction times the normal force. And then kinetic friction is the force of friction between a mobile object and a surface. Here's the equation for kinetic friction. It's just the coefficient of kinetic friction times the normal force. And these coefficients of friction, they're unique for each material.
In our experiment, we're testing the coefficient of friction of different objects and different masses to see the relationship between like a material of an object and the coefficient of friction, and the mass of an object and the coefficient of friction. So how we did that was we took a clipboard and we put our object at the top of the clipboard and lifted it up until it started to move. And so we measured like the length of the clipboard and the height of the object because we want to solve for our angle theta. So we can analyze this with a free body diagram, and here's the free body diagram. You have your force normal going perpendicular to the clipboard, force gravity going directly downward, and force friction opposing the motion going this way. So with trig, you can use this theta to solve that the this y component of the force gravity is equal to mg cosine theta, and the x component opposing the force friction is mg sine theta. So we derived a few equations here. We know that the force net in the y direction is 0 because the acceleration in the y direction is 0. So we know that it has to be the force normal minus the mg cosine theta that we got from our trig. So we know force normal equals mg cosine theta. So the net force in the x direction is equal to the x component of the force gravity, which is mg sine theta, and the force friction. Force friction is equal to the coefficient of friction times force normal. So we use our force normal we solved for earlier to find the force friction, which is mg cosine theta times the coefficient of friction. So our F net in the x direction is mg sine theta minus mg coefficient of friction cosine theta.
Okay.
So using the equation we just derived, we can then take it further and know that right at the instantaneous moment where theta is, we know that the F net is 0 because it's not, like this is the moment where the force friction is at its max. And so we can use that MA equals 0 and set these two things equal to each other. You can tell that mass and G cancel out, and you end up with the coefficient of friction equaling tangent theta. So the only thing that affects the coefficient here is the angle theta, which will be unique for each of our objects.
Kinetic energy is the energy of motion, and the equation for kinetic energy is 1/2 mass times velocity squared. And potential energy is the energy due to position, and the equation for potential energy is mass times gravity times height. However, for our experiment, we do not have an isolated system. Think about when you rub your hands together, they get hot, and the same thing happens when the phone or calculator is sliding down the clipboard. Energy is lost as heat when this happens, and so therefore, this equation doesn't apply for high coefficients of friction.
So for this part of the experiment, we used a calculator with the little sticky feet on the end and tried to slide it down the clipboard. It kept almost flipping off, sort of, so it clearly has a very high coefficient of static friction. In the end, we calculated the coefficient of static friction as 0.74.
Once the calculator starts moving, two things are happening. One, the potential energy is being transformed into both heat and kinetic energy, and two, the force on the calculator is no longer static friction, but kinetic friction. So because the potential energy is not only turning into kinetic, that's why the calculator keeps slowing down and speeding up. Because of the kinetic friction, there's a net force on the object, so it's decelerating, and the heat created between it does not allow an equal transfer of energy.
This is the plot of the calculator with the little sticky feet. The position plot clearly shows that it struggled on its way down. It kept stopping and starting if you look at the chart down below and find the velocity. The angle, however, was fairly consistent. So for this part of the experiment, we used a phone with a very smooth case, and as suspected, it had a very high coefficient of friction. We knew this was going to happen because the case has been smoothed down, so it has more points of contact with the clipboard. The coefficient for friction that we found was actually 0.713, slightly smaller than the coefficient of friction for the calculator with the sticky feet. This is our plot of the phone with the case. As you can see, it was very choppy on the way down. The phone kept stopping and starting. That was due to the friction. But you can find our theta down below. And our velocity is also very inconsistent, but that makes sense if you look at the graph because velocity is the slope of a position graph. For this section, we used the other side of the calculator without the little sticky feet, and as you can see, its coefficient is much smaller. It slid a lot faster than the phone with the case or the calculator with sticky feet. If you look at the graph, the plot we have, it's a position time plot, and you can see that it's pretty steadily decreasing, and then all of a sudden it swoops down. If you look at the velocity, we showed you the section of the velocity chart at the very end of the experiment, so you can see how it's slowly, the magnitude of the velocity is slowly increasing, but it's in a negative direction. And you can also look at the theta, and we use that theta to calculate our coefficient of friction, which is 0.45. Our fastest experiment was the phone without a case at 0.34. The experiment with the lowest coefficient of friction was the phone without a case. It also worked the best with tracker. If you look at the neat little arrows it created, it worked so well with tracker because it had the most smooth position. It flowed very nicely, and you can see that in the graph as well. If you follow its velocity on here, it's moderately more steady than the rest of the velocities. Still pretty choppy though. So this final part of the experiment really helped support our hypothesis that the phone without a case would have the lowest coefficient of friction. And we figured that out by the basic materials, namely the sticky feet on the calculator, which are specifically designed to help it from rubbing off of surfaces or damaging the calculator. So you know that has a very high coefficient of friction. And also the back of the cell phone with the case, it's been rubbed so fine and so smooth that, as we were talking about earlier, it has more points of contact, and so it's going to have a higher coefficient of friction.